So for those who are new to open air clouds, there's a little bit of information about what our organization is and what it is about. We were founded back in 2018, and we are essentially arising out of the spatial computing industries, a lot of professionals, a lot of startups, some organizations that came together because we're very passionate about having open and interoperable approaches to this new technology area. So we want to drive the development of those standards and protocols that can help achieve that, to connect the digital and physical worlds. And also we care very much about topics such as privacy, control over private and sensitive data, also on the government level, or other kinds of such data that needs to be managed properly, safety, security, accessibility. So we want this type of technology to really help benefit everyone, and have a thriving ecosystem that is prosperous for all the participants. So we got 300 individual members, over 60 partner organizations. And also last year we created a subsidiary in Europe. Alina Kadlowski is on the call. She is the managing director of the European branch. And I think now it's time for James Jackson to go through the platform I've been speaking about.
Thank you, Jan-Erik. So I'm going to touch on the high-level architecture for the Open Spatial Computing Platform, or OSCP as we call it. One of the key goals of OSCP is for us to create open source reference implementations for the core components that you see here. And hopefully you'll see today that this is an area where we've been making good progress. On this intro slide, I want to cover a couple high-level areas. Firstly, the color coding. You'll notice that there are certain elements or components that we say are fully specified by OSCP. And so what this means is that not only are we specifying APIs and data models, but also the inner workings of that particular function. There are other elements that are partially specified. Those are geopose service or positioning service as an example, and the reality modeling service. Partially specified for us really means that we're focused on the interoperability aspect. So we're focused on standard APIs and data models, but not necessarily the inner workings of the implementation. So there may be different implementation options. Some may be open, some may be proprietary, but the key goal here is that they're all able to interoperate. Lastly, there are a couple elements here shown in orange that are not specified by OSCP, but they are an important part of the overall mix in terms of delivering the end-to-end experience. Those are really around the content hosting and any cloud rendering services, right? So our focus is primarily on bridging between the real world and the virtual world. So spatial service discovery, geopose, and reality modeling, which I'll touch on here. Now, in terms of where these elements reside, we'll start from the bottom. Let's assume that we've got a user with a 5G connected AR or smart glasses. That device would most likely be running an OSCP SDK or library that facilitates simple communication with all of the OSCP services shown here. Now we have a set of services that live in a particular locale or geozone, as we call it. This could be a city or a town. We assume that these would generally be located close to the end users, and as such, most likely resident in some sort of an edge cloud. Now above that, at the top level, we have spatial service discovery. So this is a bit like a DNS hierarchy. You could think of this as being similar to a country top-level domain. So spatial service discovery would most likely be operated by a foundation at the country level. And spatial service discovery essentially allows you to discover all these other services that are within specific sub areas. So it's really an association of coverage polygons and and services. And so I'm going to step through the sequence of interactions that a typical client would follow here. And we start off, the very first request would be to spatial service discovery, right? So the client would provide some coarse information about its location. It doesn't need to be very precise. And it would get back information about available spatial services in its area, as well as their specific coverage zones, right? Once it has that information, the next step for it is to connect to the geopose service to determine this geopose. Now, geopose is essentially a highly accurate representation of the position and orientation in a common real-world coordinate system. And we've been working with the Open Geospatial Consortium on standardizing this representation. Now, in addition to the standard representation, we've also defined a standard API that allows you to communicate with the geopose service, which is essentially a positioning service. Today, most of these are visual positioning services, but they could certainly include other technologies like 5G positioning, for example. So several of our partner companies that provide visual positioning services have already implemented support for this standard geopose protocol. So essentially, the client is streaming sensor data such as images and GPS information and getting back its accurate geopose. Right? Once we have the geopose, the next step is finding interesting spatial content around us. That could be 2D or 3D assets that have been placed around us. It could be richer spatial experiences where there is a particular jumping off point in the real world to enter those experiences, right? Spatial content discovery, actually also spatial service discovery, are both designed in a distributed or decentralized manner. So the idea here is that you have multiple providers that that operate together in a peer-to-peer mesh and essentially contribute to a common shared spatial index. So in a way, this is sort of like democratizing search for the spatial web. The idea is if you have a piece of content and you make it public, that content should be available to anyone regardless of which service they're connected to. So we are trying to avoid this idea of having different silos depending on services. Now, within spatial content discovery, we have just lightweight JSON records that essentially have references to content that may be externally hosted, as shown over here. And there's also the geopose associated with the content itself. So we can accurately place it in the real world. And we'll see more information on that as we go. The final step that's of interest to OSCP is how we get this content to seamlessly interact with the real world. The reality modeling service is really where this idea of a digital twin comes into play. That digital twin would include both static information like buildings and roads, as well as dynamic information like people and cars. So there's a concept of crowdsourcing information to create this model. And of course, you can also subscribe to the model. And the idea is that we would have a standard protocol that allows for this structured representation of reality to be served to a client. The simplest early use case of this would be something like occlusion. So let's imagine that I've now discovered the content from spatial content discovery, but there's a tree that's between me and some of that content. So I need to be able to tell the device not to show me the content that's blocked by the tree. right? Now, I mentioned here that spatial, the actual hosting of the content or cloud rendering are not really inside the scope, but of course, those come into play in terms of delivering the final experience to the client. So I'll touch a bit more on a few of these specific services. You'll recall that I mentioned the top level service here is spatial service discovery. And you can see here that you've essentially got 2D coverage polygons, and then there are associated services with those. Here I'm showing the GitHub repository that has the code for the core spatial service discovery service, as well as the GitHub repo for the client library that facilitates simple communication with this service. There's also a working prototype of it hosted here, and I'll quickly show this at the end. The other one was spatial content discovery. So this is the one that allows me to discover the spatial content that's available within a geozone, right? So you'll notice that in this case, we've pulled in a GLTF of Bender and his geopose, and we've been able to place him into the scene correctly. Again, as with service discovery, there's the repository for the code of the core service, as well as the repository for the client library, and there's a running prototype that you can interact with. In terms of the prototypes, if you want to create new data, you would need an account, but anyone is able to read the data to understand the current model. And this last one that I'm touching on is the geopose protocol, right? So I mentioned that there is a standard geopose representation that we're working with OGC on. And then there is what is essentially a localization protocol. So this allows you to stream sensor data from a variety of sensors into a positioning service and have it return your geopose. And you can see the repository here that defines that particular API. As I mentioned, several partners, including Augmented City and Immersal, have already implemented support for that geopose spec. Several of our partners have also integrated with the spatial service discovery and spatial content discovery services. There are some demos and clients that I'll just reference here, and if people have time, they can certainly look at them offline. At this point, I will take a quick minute and jump. Okay, so I'm going to drop out, and I will show you a couple of the services here. So the first one, spatial service discovery. This is essentially allowing you to interact with the RESTful APIs. It's fairly straightforward, and what we'll do here, we'll specify the country. As I mentioned, this is operating at the country level, and we're specifying a course position, which we use something called H3 hexagon to sort of provide this location area. So essentially, we do a query here, and what we see coming back is a list of the specific services that are available. There's the contact information for connecting to those services and the associated coverage polygons for those services. And this is a standard GeoJSON representation. Similarly, if we look at spatial content discovery, there's a concept of themes or topics where we can control synchronization of data by topic when we have different providers synchronizing. So here we're going to look specifically on this history topic. Once again, we're specifying a course position with an H3 index. And we'll get back the spatial content that is available to us. Here, as an example, you'll see that we've got a 3D model of a cat, which is being provided both as a GLTF and a USDZ, so that we can support multiple client types. And here you'll see the geopose that is associated with that content. The last one I will show is an example of geopose. And what we're essentially doing here is we're starting with an image, and we have the GPS information for that image, and we're going to localize it. What's actually happening behind the scenes is that it's first communicating with Spatial Services Discovery, providing that GPS information, or rather the H3 representation of position, and it's going to find its geopose service. It'll then provide the GPS and image data to the geopose service, and it'll get back its geopose. So we'll do a localization. And here you'll see the geopose that was returned. So this is actually communicating with one of our partner services, Augmented City. And they have a pre-built map of the particular area, so they're able to accurately localize this image into that map and return the standard geopose. Now we can place this representation onto a real-world model. And what you will see here, so now we're seeing the image. If I zoom this out a bit, you'll notice that that image has been nicely aligned with the 3D model in terms of the specific buildings and where it is exactly located. So that's all I wanted to show.